Well, hi there. Thank you for showing up for your learning. Today we're looking at annuities, mortgages, loans, these types of products. And there are some minds-on activities in the handout that you can take a look at, and we will do these on Wednesday. All right. For now, let's take a look at the future value of an annuity. An annuity is where you make regular payments into some compound interest-bearing account or investment product. This is a very common investment strategy because it's rather uncommon to have, say, $1 million right now that you want to invest for the future and not be planning on making further investments down the road or whatnot. Whereas, say, taking a certain percentage of your paycheck every week or every month and making that investment into your investments, uh, that's much more common. And when we do that, it creates a geometric series. The deposits we make today will earn interest more times than the deposits we make a month from now, or 2 months from now, or 1 year from now. Will be fewer and fewer times that those things have earned interest, and that creates that geometric series. And we need to add together the value of each individual deposit to generate the value of the full investment. So, in these cases, the future value of these investments is going to be equal to this formula here. R is the regular payment that you're making every compounding period. So suppose that your interest is compounding monthly. We would want the total monthly payment that you are making into your investment right there. And then in here you have your growth factor per compounding period. This is 1 plus your interest rate divided by the compounding frequency. And we're going to raise that to the power number of compounding periods, which is compounding frequency multiplied by years. We subtract 1 there, and then we're going to be also dividing by your growth factor, your interest rate per compounding period, which is R over C. Now that's a lot of arrows. Let's take a look at one way that you'll sometimes see this formula written down, which looks a lot simpler. We would say future value is equal to R multiplied by 1 plus the interest rate per compounding period minus 1, all divided by the interest rate per compounding period. In this case, the only thing different here is I have replaced R over C with the interest rate per compounding period, not per year, and C multiplied by T is the total number of compounding periods. So that's a way of writing it down in a way that looks simpler, and you can work with whichever way you like. I kind of like working with it that way. So let's go and answer some questions with this tool. All right. So if we know $100 is invested per month for 12 years, a 12% interest compounded monthly, how much would be invested in total? So we want to know the future value of this investment strategy. What would be how much will be invested? Like how much would we be paying in? What would be the final amount that we would have in our investment product? So that would be the future value. And how much interest total would be earned? Basically, how much have our investments grown? My prediction is that if we did this for 12 years, we would be looking at about doubling our money overall. So let's see what we get. My first suggestion is we're going to write down a little list. Future value. This is we want to solve for, so we don't know that. Our R is our regular payment, so let's write that down. It's $100. We're going to invest that every month. Our little r, is our interest rate, and I told you that's 12%, which is equal to 0.12. And C's compounding frequency, it's monthly, so that's 12. And T, time in years, also 12. Okay, lots of 12s here. So let's go ahead and use our formula. I'm going to use this formula up here, which will look like this. We're working black. Future value is equal to the regular payment multiplied by 1 plus R over C all raised to the power CT minus 1 and the bracket, all divided by R over C. Okay, now let's substitute in. We have our handy dandy chart over there. We can substitute it in. Future value is equal to $100. That's the regular payment we're going to make each month, multiplied by 1 plus R over C. Well, R divided by C is going to be 1% per month. This is 12% per year. So we will have 0.01 and the bracket, all multiplied by CT. Well, C times T is 12 times 12, so that will be, well, I could write down 12 times 12, or I could write down 144, because that's 12 squared, minus 1. And that bracket, all divided by R over C, and that's, again, 0.01. All right, so now we work in Bedmas order, and I'll show you on the calculator how I work this in Bedmas order. Start with the most internal bracket, 1 plus 0.01. So that is 1.01. Raise that now to the power 144, and that will be equal to, about 4.2. Okay, you're going to subtract 1 from that, and that equals this number. Then we multiply, and so now we've done everything inside this bracket here. Now we're ready to do this multiplication and that division in any order. You'll also notice that that multiplication and that division have the same effect. So anyway, we're going to multiply our answer here by 100 equals, and then we're going to divide it by 0.01 equals. Okay, so we're going to have about $32,000. So the future value is 31,906.16. Let's go with 31,906. We're around there. Future value is $31,906. So for the low price of $100 for 12 years, $100 per month for 12 years, you could get yourself $30,000 with an excellent interest rate and a lot of consistency with making those deposits. Now let's see, how much did we invest in total? How much did we pay in? Well, we were doing $100 per month, and we did that for 12 years per month, 12 months, so that's 144. So we invested a total of $14,400. And what did I say? We'd about double our money? Yeah, we about doubled our money. Okay, our future value is much greater. If we had made this whole deposit up front, we would have more money because the whole amount of money would have earned interest for longer. Only $100 was earning interest for the whole time. That was our first deposit. So that's why it's a little less than if we had made the whole deposit up front. I think it's going to be about 4 times our money if we do the whole thing up front instead of 2 times our money. Okay, so let's figure out how much interest we had. To do this is like the total. This is like the regular deposit times the number of compounding periods. If we do the future value minus the total number of deposits, then that would give us the amount of interest that we have earned. So we would do 31,906 minus 14,400, and that's going to equal, just going to take away 14400. Oops, I did an extra 4 in there. There. And there's our interest, 17,506. So we earned $17,506 in interest. Cool. All right, so that's how you use this tool, solve a problem like that. Now we can also answer questions like this. How much would you have to save every 3 months to have $100,000 in 20 years, earning 8% interest compounded quarterly? Again, my first step is always going to be to make a little chart. Future value is actually known. I know I want to have $100,000. My regular payment is my unknown. How much would you have to save every 3 months? Okay, my compounding period is quarterly, And fortunately, we're going to make these payments every 3 months, so that is quarterly. So C is 4. My little r interest rate is known, it's 8%. So that's equal to 0.08. Okay. And T for time, 20 years. 20 years is going to be 80 compounding periods. All right, so let's now take this question apart. My suggestion is when you notice that you're solving for one of your variables that is not usually the one that you express this as solved for, rearrange your formula in terms of that first and then sub in. It's a little nicer than subbing in numbers. So I'm going to copy it out. Future value is equal to the regular payment multiplied by 1 plus r over c raised to the power ct minus 1 and that big bracket all divided by r over c. Check to see that you have the correct formula. Yes, I do. And then rearrange your formula to solve for r. So the first thing I'm going to do is multiply. Let's get our inverse operations pen out. Going to multiply by the thing on the bottom, r over c. And we're going to do that on both sides, r over c. So we're going to have here future value multiplied by r over c. And then we're going to divide both sides by, well, I'll show you in just a second. This is going to be equal to r times 1 plus r over c and the brackets to the ct minus 1. Okay, we just want to solve this for r. So we only have one more inverse operations to do. Hoopity day. We're going to divide by that great big bracket. 1 plus r over c to the ct minus 1. Okay, divide by that both sides. And it's at this point that you might say, Mr. Jennings, why are you bothering to write that whole thing out? Why don't you just cancel it this way and then write it down here? Well, that's a good question. You could absolutely do that. And then let's write our new formula in purple. We're going to have r, this r, is equal to, and I'm just switching the sides because I like to say r equals rather than blah, 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 equals r. R equals the future value multiplied by r over c divided by 1 plus r over c to the ct minus 1. Okay. I don't have to have those square brackets, but I will just for clarity. Now I can just plug in these knowns and solve directly for that unknown without any inverse operations necessary once I get numbers involved. Just do it with your letters. It's a little bit easier. So let's go. Let's do it. All right. So the amount that we would need to save every month is given by R is equal to 100,000, because that's the amount of money we want in 20 years, multiplied by R over C. So that's, I'm going to put this in brackets, 0.08 over 4, okay, divided by 1 plus R over C, which is 0.08 over 4. And yes, if you're just directly writing down 2%, 0.02, then that's also fine. Raised to the power CT. So C is 4 and T is 20. So that's going to be 80. The exponent will be 80 minus 1. And now we can simplify a bit. R is equal to 100,000 times 2%. 100,000 times 2%, 2% of 100,000 is 2,000. So I'm going to simplify that, do some mental math. 2,000, it's comma. That's the numerator. So it's multiply here. It looks like minus, but it's actually a multiply. 1 plus that, so that's 1.2%. Sorry, 1.02. That's 102%. Raised to the power 80. Can't do that in my head. Minus 1. That now we can punch in the calculator in just a few steps. So let's do it. Clear. All right. This will be our regular payment. 1,000 divided by, put this in brackets, 1.02 raised to the power 80 minus 1, end the bracket, equals $258. $258. So R equals $258.04. So for the low cost of $258 per 3 months, and you get 8% interest compounded quarterly, and you do this for 20 years, less than $100 a month, you'll have $100,000 in 20 years. That's pretty cool. Now, $100,000 might not be enough to retire, but you'll only be in your 30s and you'll have $100,000. It's pretty cool. Keep going, and you might have enough for retirement by your 50s or 60s. And actually, to test how much money you would have if you kept going, we could dump this all into Desmos. So anyway, that's how this one gets solved. So then let's do our therefore. Therefore, you need to. Why do I do that this way? Let's do it typing. I'm much faster, and it's much neater. Therefore, you need to deposit $258.04 every 3 months to have $100,000 after 20 years, given 8% interest compounded quarterly. There you go. There's our therefore statement. Beautiful. All right. So here's some textbook practice that you can do. You can also practice in Desmos. But now let's take a look at present value of an annuity. Sometimes we do the same thing that we just did, but backwards in time, where we want all the money now and we'll pay for it in the future. These are loans, where the amount that you borrow starts earning interest, and then as you make payments, it eats into the loan and so slowly reduces it to zero. Towards the beginning, your payments are mostly covering interest, but as you whittle away at the principal that you borrowed, eventually all your payment will wipe out the loan and put it down to zero over time. This requires a rearrangement of the formula that we're not going to go into, but the new formula looks like this. And again, CT, that number up here, that could be written as N, as the number of compounding periods, and R over C, that number there, could be written as I, the interest rate per period. But I like writing the formula this way. Okay, so another way that you can use this would be to say, let's say you had that $100,000 that you acquired here through your savvy investment strategy, and you wanted to then, in your 30s, make regular withdrawals from that over time in order to fund your lifestyle. You don't want to use it all at once for a single car purchase. You're going to take out $10,000 every 6 months or something to support your lifestyle. This math works out the same way as a loan. So let's go. Here is our new formula. Let's go ahead and rearrange the equation for R so we can solve two different types of problems. So here I'm going to multiply both sides by R over C. And so I'm going to have PV times R over C. And then that's going to be equal to all this stuff on the top, because this has been moved over by multiply both sides by that. And so now all I need to do is divide by this big chunk, and I have solved it for R. So if you can start doing these in your head, that's fantastic. So this would be PV multiplied by RC all over 1 minus 1 plus R over C, and the bracket to the negative CT. This has a negative exponent in it, and that will be equal to the regular payment. So here is another rearrangement of that formula that is also true. If this is true, then that's true. Okay, let's go. Let's use it. How much money must be invested now to withdraw $10,000 every 3 months for 20 years. Cool. At 6% interest compounded quarterly. Okay. So the thing is, like, that interest is actually helping support your money. So as you make withdrawals, you're withdrawing some interest and you're withdrawing some principal, so that eventually the money will run out, but it will last a lot longer than it would without the interest. Okay, so our regular withdrawal is $10,000. Fill in your little chart. Our interest rate is 6%, which is equal to 0.06. We are compounded quarterly again, so C is 4, and time is again 20 years. Let's go ahead. Our present value, the amount that we need to invest presently is given by the formula. So PV is equal to the regular withdrawal or the regular payment on a loan multiplied by, I think it's 1 minus, let's just try it. Let's try my memory. 1 minus bracket 1 plus R over C to the negative CT, big bracket, all over R over C. Let's see if I got it right. I did! Whoa. Memory for the win. Short-term memory. Okay, so now let's go. Let's plug in our knowns. So present value, the amount that we need to invest right now to withdraw 10 grand every 3 months for 20 years to support our lifestyle, is equal to 10 grand, substitute in for R, multiplied by 1 minus 1 plus R is 0.06 divided by 4 raised to the power negative, C is 4, negative 4 times 20. So that's going to be a negative 80 exponent. Wow. All divided by R over C, which is 0.06 over 4. Cool. Now let's work out those little bits. Present value is equal to 10 grand multiplied by 1 minus, not much we can do there, 1 plus 0.06 over 4. 0.06 over 4 is equal to 0.015. Calculator will tell you the same thing. So inside the brackets, we will have 1.015 raised to the negative 80, all divided by 0.015. Now, calculator time. Nothing left here for mental math, I'm afraid. Not at my level. So bring your calculator somewhere it's useful to you. Clear everything and start punching from inside the bracket. The first thing that we're going to do is raise 1.015 to the 80, but it's negative. 80, but it's negative. There we go, 1.015 to the negative 80. And that's equal to this number. And then we're going to subtract it from 1. So here's a trick. I have a positive number here. I make it negative, and then I add 1 to it. That's 1 minus that thing. Now I take that number and multiply it by $10,000. And that's the numerator right there. Ooh, it's going to be a lot of money we need to get this to go. And then we're going to divide by 0.015 equals. So, in order for us to have $10,000 every 3 months for 20 years, we need nearly $500,000. Ouch. The present value required is equal to $464,073. Okay, so let's write a therefore statement. Therefore, in order to make a regular withdrawal of Morning.
Hi, Mr. Jennings, how are you?
Very good. How are you doing? So in order to make a regular withdrawal of $10,000 every 3 months for 20 years, you earning when you earn 6% interest compounded quarterly, you must invest $464,073 up front. So that's about three and a bit $1,000 per month. So this is roughly equivalent to like cash for life. If you won cash for life, which is $1,000 a week for the rest of your life, and the rest of your life for 20 years, then that would be a value of about $500,000. There you go. Now, let's take a look at perhaps a more relevant to your life type of problem. If Kareem is purchasing a used car for $7,500 and he wants to repay the loan with monthly payments at 4.5% compounded monthly, and he plans on paying off the loan in 3 years. So what will his monthly payment need to be? And how much interest will he pay in total? Okay, let's go ahead and figure this one out. First, our present value is just the value of the car, $7,500. Our monthly payment is our unknown, so we want to use the rearrangement of the formula for R. We know time is 3 years, compounding period is monthly, 12, and the interest rate is 0.045. That's 4.5% as a decimal. We got all the things we need. Let's see if I remember the rearrangement for this formula. R is equal to, no, I don't think oh, maybe I do. Okay, is equal to present value multiplied by the interest rate over C, all divided by 1 minus, I think I got it, 1 plus R over C raised to the negative CT. Okay, I think that's the rearrangement. I'm kind of just rearranging the formula in my head to do that. I don't have it memorized. That looks good. That's that. Yeah, so now we plug in our knowns and get our unknown, which is the regular payment that we're going to have. So regular payment will be equal to $7,500 multiplied by 0.045 divided by 12. Let's put that in brackets so we remember that's a multiplication. 0.045. That's a 4. Let's zoom in so I can write bigger and don't have to write janky numbers. Oof, that's a big erase. 0.045 over 12. All over, big bracket, not necessary, but sure. 1 minus 1 plus 0.045 over 12, and the bracket to the negative CT. And C is 12, so that's 12, and T was 3, so that's going to be negative 36. Let's simplify. Zoom out a little bit. It's a little zoomed in. Okay, the regular payment will be, let's see, do I have any cancellations I can do there between 7,500 and 12? Yes, indeed there is. They're both divisible by 3, so I could do that if I wanted, but let's actually simplify this one. It's going to be more useful. So 45 over 12, I can take out, again, just a factor 3. So that's 0.015 over 4. And I'm just going to do it on a calculator, man. I'm going to actually simplify that to the interest per period. 0.045 divided by 12 is an integer. Well, so it's a non-repeating decimal, so I can write it down exactly, so without losing any detail. So that's 0.00375. Okay. All divided by 1 minus 1.00375, because I just add 1 to that same number, raised to the negative 36. Okay, so let's do the numerator. So we got that number right here. I'm going to multiply that by 7,500 equals this number, 28.125. So we can write that down. 28.125 is the numerator, and it's in dollars. And then 1 minus, let's do that number. Let's actually just do the whole thing on the calculator. Clear. 1 minus 1.00375 raised to the 36, but it's negative, equals, this is the denominator, 0. I'm just going to write that out, 0.12606. 0.12606. So it looks like you only need to pay $28 a month, but actually I got bad news for you. You got to divide that by a small number, which makes it bigger. So here's the trick. Okay, I want to divide by this number, so I can raise this number to the 1, but it's negative, and multiply by that number is the same thing. That number times 28.125 is my regular payment, or 223.11. No, 223.10. So for the low price of $223 a month, you can afford a $7,500 car in 3 years. So these are our new topics. Some lessons that you can, I'm going to have to put the homework into that. And also try the Delta Math. Any questions, hit me up by email, and check also the Delta Math walkthroughs. Thanks everyone for showing up for your learning on this snow day. Bye for now.